All right, let's dive right into acid-base titration. It's one of those classic cornerstone techniques in chemistry. We're going to explore exactly how this method lets us figure out the hidden strength of a solution, pinpoint that critical moment of change, and then use a little math to reveal the final secret. So let's get to it. So picture this. You're in a lab and you've got a beaker full of some acid. You know what it is, sure, but you've no clue how strong it is. How do you figure that out? Well, that's the mystery we're solving today. We're basically on a quest to find a hidden number, using a technique that's absolutely vital everywhere, from making sure products are safe to running tests in hospitals. Okay, before we jump into the lab and start mixing things, we really need to get a handle on the theory. What's actually happening at the chemical level when we do a titration? At its heart, you can think of acid-base titration like a detective story. We have our mystery solution, an acid or a base of unknown strength. And to figure it out, we bring in a witness that we know everything about. That's our standard solution. And by reacting them together, we can get our mystery solution to reveal its secrets. The whole thing works because of one simple, elegant reaction: neutralization. You take a hydrogen ion from the acid, an H+, and it meets up with a hydroxide ion from the base, an OH-. And what do they make? Just water. That's it. That's the secret. By controlling this reaction perfectly, we can find the exact moment when all the acid has been used up. Now, this is a really important distinction you have to get. There are two key moments here. First, there's the equivalence point. That's the perfect theoretical moment when the amount of acid and base are chemically equal. The problem? You can't actually see it happen. So that's where the end point comes in. This is the moment we can see thanks to an indicator we add that changes color. The whole trick of a good titration is picking an indicator that changes color right around the same time the equivalence point is reached. That makes our visible clue super reliable. And here it is, the key that unlocks the whole puzzle. M1V1 equals M2V2. This simple little equation is so powerful. It connects the molarity, or M, and the volume, V, of our two solutions. As long as we know 3 of those values, we can easily solve for the 4th one, which is, of course, the concentration of our mystery solution. All right, we've got the theory down pat. Let's switch gears and get practical. It's time to walk through how you actually do one of these experiments in the lab, step by step. First things first, let's get our gear together. You're going to need a burette, which lets you add liquids very precisely, a pipette to measure out your unknown solution perfectly, a conical flask for the reaction to happen in, your chemical indicator, your standard solution, the one you know everything about, and of course, the unknown solution you're investigating. Okay, the actual procedure is like a little 6-step dance. Step 1, prep your burette. Make sure it's clean and, critically, that there are no air bubbles hiding in the tip. 2, use your pipette to put an exact amount of the unknown into your flask. 3, add just a few drops of your indicator. 4, start the titration. Add the solution from the burette while constantly swirling the flask to mix it. Now here's where the skill comes in. As you see the color change start to hang around for a second before disappearing, you need to slow way down, like drop by drop. 5, the second you see a permanent color change, stop. That's your endpoint. And finally, step 6, carefully record the final volume from the burette. Every single drop matters. So we've done the hard work in the lab, we've carefully collected our data, and now it's time for the moment of truth, the big reveal. Let's do the math and finally uncover the concentration of our mystery solution. Let's just walk through a quick example so you can see how easy it is. Let's say we started with 25 milliliters of our unknown acid. And to get that color change, it took exactly 20 milliliters of our 0.1 molar sodium hydroxide standard. We just pop those numbers into our formula. M1 times 25 equals 0.1 times 20. Do a little bit of algebra, and we're there. And the answer is 0.08 molar. And just like that, with some careful work and a simple formula, we've solved the mystery. We know the exact concentration of our unknown acid. Mission accomplished. Okay, so we found our number. That's great, but why is it so incredibly important to get that number exactly right? Let's pull back from the lab bench and look at the big picture, why accuracy is king, and where this technique actually gets used in the real world. Look, when you're doing a titration, accuracy is everything. A few tiny common mistakes can completely throw off your results. If you read the burette from an angle, that's called parallax error, and it gives you the wrong volume. That air bubble I mentioned, if it comes out during the titration, it'll make you think you used more solution than you did. And overshooting the endpoint, even by a single drop, will make your calculated concentration wrong. That's exactly why you always repeat the experiment until you get a few results that are nearly identical. That's what scientists call getting concordant results. And believe me, that precision matters, especially in an industry like pharmaceuticals. Titration is used all the time to check a drug's purity, making sure it has the right dose of the active ingredient. It's used to standardize other chemical solutions for more complicated tests. And in quality control labs, it's a go-to method to make sure every single batch of medicine is made to the exact same safe and effective standard. So, to wrap it all up neatly, acid-base titration is an incredibly powerful, precise, and reliable tool. It's this beautiful combination of a simple chemical reaction, a visual clue, and a careful technique that lets us find a value that would otherwise be completely hidden. It's a chemistry classic for a very good reason. And that leaves us with one last, really important question to think about. We know how critical the indicator is for signaling when to stop. But what would happen if you used the wrong one? An indicator that changed color way too early or way too late? Would the concentration you calculate end up being too high or too low? Something to chew on. Thanks for joining me for this explainer, and I'll catch you on the next one.